Welcome everyone. So our third and final speaker this afternoon is Olivier Martin, who comes from Chicago. He was a student of Abelian, and I believe he's still in Chicago, right? So and he's going to talk about Abelian varieties, and their subvarieties are far from rational. So welcome.
Hi, thanks for the introduction. It's a pleasure to join the department, and it's going to be an even greater pleasure when we can meet in person soon enough, hopefully. So the thing that I want to talk about today is kind of a body of work that I did in my thesis, which all points to kind of a same question, which is how far from rational subvarieties of Abelian varieties are. So I'm going to introduce those terms, what it means for a variety to be rational, what is an Abelian variety, how do you measure how far a variety is from being rational. So of course, some of you might have heard Rob talk about this or Nathan Chen talk about this, so there might be, some of you are probably quite familiar with the subject already, but nonetheless, since it's Capsule Talk, I figured that I would explain these terms. So I'm gonna take the most simple approach. For me, an algebraic variety is just gonna be a subset of n-dimensional complex space, which is cut out by polynomial equations. So I'm also gonna ask that X can be written as a union of two proper subsets that are also cut out by polynomial equations. So let's look at some examples. I could have a cubic curve, for instance. If I take the coefficients there to be general, then it's going to be actually a smooth manifold. So it's going to be something like a complex compact torus, which is punctured at one point. Here's like the real picture of a cubic curve. On the other hand, if I look at this thing on the right, I'm not going to consider this to be a variety because it's the union of a line and a cubic curve. So I don't want to consider these kind of situations. So in algebraic geometry, we work with what's called the Ersky topology. So this is a topology where the closed sets are finite unions of subvarieties of ambient varieties. So the feature that this points to is the fact that open sets actually carry a lot of information about the ambient variety X. So an open set in particular is dense, but it actually contains a lot of information about X. So it's kind of a very rigid geometry that we're talking about. So in particular, this makes the following definition interesting. So if I have two varieties X and Y, I can say that they're birational if they have open sets that are isomorphic to one another. If I were to do that, for instance, with topological manifolds, then I would just, the two varieties would be quote unquote birational if they would have the same dimension. So this really points to the fact that this is interesting only because we're dealing with algebraic geometry. So in particular, we're going to say that X is rational if it's birational to complex space of the same dimension. So let's give an example. If I have a nodal cubic over here, I claim that it's actually birational to the complex line, so that it's actually a rational curve. So how would I show that? I need to exhibit an isomorphism between an open on the left and an open on the right. So the open on the left is just going to be the complement of this red point over here, and my map is going to be the following. To a point X, I can associate the line that goes through the blue point and the red point, and this line is going to intersect this red line at a single point, which I'm going to call f of x. So this is going to give me a map that goes from the complement of the red point on the left to well, actually not quite the complement of the red point, because the way I defined it, I have to be a little careful no, that's fine, sorry. This one is fine. So it goes from the complement of the red point to the line on the right, and this is going to be an isomorphism between an open set on the left and an open set on the right. All right, so this example that I gave you shows that it's interesting to consider maps that are maybe not defined on the entirety of the curve, but that are defined only in an open set. So this is the notion of a rational map. So a rational map between varieties, it's something like a morphism, but it's only defined on an open set of X. So here's another example. It's basically the same construction. So here I could fix the red point, and to a blue point X, I could associate the point of intersection of this line with the red line over here. And it's kind of clear to see that this is a 3-to-1 rational map. So most elements of the red line, if I fix a point f of x and I draw the blue line, is going to intersect this lemniscate in 4 points. And one of these points is going to be the red point. So I'm going to have, generically, I'm going to have 3 preimages to this map. And this one is the one where you have to be a little careful, because the way I defined it, if you were to take a blue point over here, then the line that you get would be parallel. So you see that this rational map is actually not defined just on the complement of the red point. You need to be careful, a bit more careful, and remove some other points if you define it in such kind of a naive way. So the kind of rational maps that I'm going to be interested in today are what are called dominant rational maps. So this is basically, essentially the same thing as subjectivity, but for a rational map. So we're going to say that the rational map is dominant if its image is dense. So here are two examples. The first one is a dominant rational map. I inverse the first coordinate and I square it, and I invert the second coordinate. And the second one is a non-dominant rational map. So why is it not dominant? Well, the image is going to be contained inside a curve in the plane because there's an algebraic relation between x plus y squared and x plus y cubed. So if I have a dominant rational map between two varieties of the same dimension, then just by simple topological reasoning, the generic fiber is going to be zero dimensional. And because we're doing with algebraic geometry, the generic fiber is actually going to be finite. So it's going to be something like, just a finite covering if you want. So in this case, we're going to call the degree of the rational map just the number of points in the generic pre-image. So here's an example, for instance, of a degree 3 rational map from x to y. All right, so let's get back to this question that we were asking at the beginning. So how far from rational are subvarieties of Abelian varieties? So how do we measure how far from rational a variety is? And to do that, it's useful to notice that x being rational is exactly the same thing as saying that x admits a dominant rational map of degree 1 to complex space of the same dimension. Well, why is that? Well, saying that x is rational means that there's an isomorphism between an open in x and an open in C to the same dimension. So I can just take the rational map that is basically given by this isomorphism. So this suggests that instead I could look at the existence of rational map of degree, if I don't have a dominant rational map of degree 1, maybe I have one of degree 2 or of degree 3. So maybe somehow I have a low degree dominant rational map to a complex space of the same dimension. So we're going to call the degree of irrationality of x the minimal degree of a dominant rational map to a complex space or projective space. It doesn't matter so much. So let's look at, for instance, the example that we gave, the example of the lemniscate of Gerono. So I was taking the red point over here. If instead I take the red point to be the singular point, then I get a 2-to-1 rational map onto the line. So this shows that the degree of irrationality of this lemniscate is less or equal to 2. But in fact, it turns out that the lemniscate is actually rational. So here's the rational parameterization for this lemniscate. So in fact, the degree of irrationality of the lemniscate is equal to 1. It does admit a degree 1 rational map. I mean, basically there's an inverse to this map, but I'm not going to write this out, of course. So the protagonists of this talk are going to be, so remember we're dealing with subvarieties of Abelian varieties, so I should introduce what an Abelian variety is. So first and foremost, an Abelian variety, if you want, is a complex compact torus. So you take a complex space of dimension G and you quotient by a co-compact lattice. But you also want that to be algebraic. So you also want that to have some embedding in projective space. So this turns out to be a very restrictive condition if you look at higher dimensional Abelian varieties. But for instance, in the case of one-dimensional Abelian varieties, an elliptic curve is the same thing as a one-dimensional Abelian variety, which is the same thing as a one-dimensional complex compact torus. But of course, this last equality, this is a really special thing to dimension 1. All right, so if we want to investigate subvarieties of Abelian varieties and discuss how far they are from rational, maybe the first situation we should care about is the case of curves. So what happens for curves on Abelian varieties? And one of the reasons why it's interesting to try to figure out how far from rational they are is that there's this basic fact that an Abelian variety does not contain a rational curve. So this is a fact that you might prove in a first class in algebraic geometry, or even in a first class in topology. So suppose that you did have a non-constant map from P1 to an Abelian variety. Then because pi1 of P1 is trivial, then this map would lift a universal cover. So this is basic algebraic topology. And then the rest is just complex analysis. So you have basically an entire map which has to be bounded because P1 is compact. So then Liouville's theorem tells you that this lift has to be constant. And so your map had to be constant in the first place. So this shows that you don't have any rational maps. So then the question is, how complicated are curves on Abelian varieties? How complicated are they from this point of view of rationality? So basically, maybe I don't have rational curves, but do I always have hyperelliptic curves and so on and so forth? So the first theorem in this direction is from 1989. It's by Pirola. So what he showed is that most Abelian treefolds don't contain curves with degree of irrationality less than 3. So they don't contain, so the degree of irrationality for curves is also called the gonality. A curve of gonality 2 is called the hyperelliptic curve. So what Pirola showed is that most Abelian treefolds don't contain hyperelliptic curves. So this was extended by Voisin rather recently. So what she showed is if you fix the level of complexity for a curve, so if you fix the gonality of a curve and you look at sufficiently large dimensional Abelian varieties, then most of them will not contain curves of that degree of irrationality. So most Abelian surfaces of dimension at least this gigantic number do not contain curves with degree of irrationality k or less. So basically she extended Pirola's results from hyperelliptic to trigonal, fourgonal, and so on and so forth. But the bound that she gets, as you can see, it's quite a bad bound, and she conjectured that you can do better, that there's a linear bound. And this is something that I proved in 2019. So if you look at an Abelian variety of dimension at least 2k minus 2, well, then most of them will not have curves of gonality k or less. So in particular, this implied Voisin's conjecture. Her conjecture was 2k minus 1, so I just shaved off a 1 from her conjecture. So the take-home message is that curves on Abelian varieties are far from being rational, and basically the larger the Abelian variety, the further from rational they seem to be. So good, now we understand a bit what happens with curves. So what happens with subvarieties of larger, I mean, by the way, I should say these are all lower bounds. So, you know, I don't think there's very well understood upper bounds for the gonality. I mean, maybe I should be precise. You know, of course you can find curves of very, very high gonality, but there's no, I think, known upper bound for the minimal gonality of a curve on a very general Abelian. So what about larger dimensional subvarieties? So if I look at surfaces and treefolds and Abelian varieties, are they themselves far from being rational? So of course you'd expect, you know, probably that's the case. If it happens for curves, then probably should happen for larger dimensional varieties. And of course, also a lot is known about subvarieties of Abelian varieties. So it's known that most of them are going to be of general type and so on and so forth. But this degree of irrationality is kind of a slightly different question. So there's a result, but from Azati and Piora from 1992 that is concerned with Abelian varieties themselves. So of course, Abelian varieties are subvarieties of Abelian varieties in kind of a trivial way. So if you just look at a whole Abelian variety, then the degree of irrationality is at least the dimension of A plus 1. So the larger dimensional, the further from rational they are. And what I proved with Colombo, Naranjo, and Pirola is that if you look at most Abelian varieties of dimension at least 3, they're not going to have d-dimensional subvarieties with degree of irrationality less than d plus the dimension of A plus 1 over 2. So basically, if you look at most Abelian varieties, their subvarieties are going to have a large degree of irrationality, and the degree of irrationality is going to grow with the dimension of the subvariety and with the dimension of the Abelian variety. So in particular, this gave us a lower bound on the degree of irrationality, which applies quite generally. So all you need is that this most is really kind of very important, of course. But we get this lower bound on the degree of irrationality, which improves on this lower bound of Azati and Pirola. So the take-home message, yeah, as I said, the subvarieties of Abelian varieties of large dimension, they're far from being rational, and the further the dimension of, larger the dimension of the Abelian variety, or the larger the dimension of the subvariety, then the further from rational they are. So the last kind of sub-question that I want to address is what happens what happens to the degree of irrationality for Abelian varieties in the simplest case, basically. So the case of Abelian surfaces. So the case of elliptic curves are double covers of P1. So this is not a particularly complicated case. So what happens in the case of Abelian surfaces? And so Alzati Pirola, I remind you, they show that the degree of irrationality is at least the dimension of A plus 1. So that would be 3 in the case of Abelian surfaces. And Tokunaga and Yoshihara actually showed that this bound of 3 is sharp. So if A contains a smooth genus 3 curve, then the degree of irrationality is indeed equal to 3. So the upshot of that is there are plenty of examples of Abelian surfaces with degree of irrationality 3. So what Yoshihara asked in 1996 is if there are Abelian surfaces with degree of irrationality greater than 3, and he also asked if isogenous Abelian surfaces have the same degree of irrationality. So I'll just remind you that if you have 2 Abelian surfaces, they're written as some quotient of C2 by some co-compact lattice. If the co-compact lattices are commensurable, so when you tensor them with Q, you get the same lattice, then we call the quotient isogenous to one another. So an isogeny basically is it's a surjective morphism between Abelian varieties with a finite kernel. What Chen did, so Nathan, so our Stony Brook's very own Nathan, so he managed to show kind of the opposite. So this is the question is, are there Abelian surfaces with large degree of irrationality? And of course, it's interesting to try to ask, is the degree of irrationality unbounded for Abelian surfaces? So this was a conjecture of Bastianelli, De Poy, Einlasersfeld, and Ullery, and what Nathan showed is that actually this is not the case. So every Abelian surface has degree of irrationality less than or equal to 4. So the part that was due to Nathan alone was that the degree of irrationality is very general. So most abelian surfaces have degree of irrationality less than or equal to 4. And then with Stapleton, they managed to extend it to all abelian surfaces. So what my contribution to this question is that so the upshot of this situation of Nathan's theorem was that because of Alzati and Pirola and Nathan's result, we know that every abelian surfaces has degree of irrationality 3 or 4. And there were plenty of instances of abelian surfaces with degree of irrationality 3. And what I managed to show is to rule out, I mean, it was widely believed that most abelian surfaces had degree of irrationality 4, and I managed to prove that. So if you have an abelian surface that has a degree of irrationality 3, then you actually get some kind of condition on the narrow severity pairing. So if you look at intersection of divisors on the abelian variety, then you have to be able to obtain the number 12 from in the image of the pairing of the narrow severity, of sim2 of the narrow severity. So this answers both questions of Yoshihara. So this shows that indeed there are abelian surfaces with degree of irrationality greater than 3. In fact, most abelian surfaces have degree of irrationality greater than 3. And it also shows that isogenous abelian surfaces do not have the same degree of irrationality. So it answers both of these questions. And so the last slide is kind of a shameless plug for the AG seminar. So I'm going to be talking next week in the algebraic geometry seminar. And what I'll talk about is an extension of this result that I just mentioned. So this is kind of recent work that I did in my thesis. And what I managed to do is, so remember, this is about the degree of irrationality of abelian surfaces. So most of them have degree of irrationality 4. So what I managed to do is to extend that to the case of abelian varieties of arbitrary dimensions. So I can show that most abelian G full have degree of irrationality at least 2G. And it's the same kind of condition basically, but I get a result which is not quite as good. So what I get is that there's an integer which is quite large, such that if I have a very general 1D2 DG polarized abelian variety, then it has degree of irrationality at least 2G. Oh, sorry, I didn't write the condition there. So as long as DG does not divide MG, then this thing has degree of irrationality at least 2G. So again, and I mean, I'm excited to hear what people have to say about, because the proof involves kind of a result about abelian varieties that seems like it should be obvious, but it took me quite a bit of pain. So I'm excited to hear if you guys have an obvious proof for it. So I think this is it. And yeah, again, thanks for your attention and look forward to meeting each and every one of you.
Well, thank you very much.